But what's the deal with baryon asymmetry? Basically, the theory that matter and antimatter aren't, or not theory, but the fact that they aren't equal in the universe. Like, is
Yeah.
there anything now that we know that maybe would, like, enlighten that question for us, like a little bit?
Yeah. So there is in fact one very standard theory now that would explain why we actually have this asymmetry. And this actually goes back to the early universe, and what we call inflation. Right?
Yeah.
There is this model where very, very early on, the universe was very, very tiny. It was in a very specific quantum state, and then all of a sudden there was a phase change, and that in that phase change, there was a non-equilibrium process where all of a sudden the universe grew very, very rapidly in this sort of non-equilibrium state. And there were interactions between the particles that were not that had an asymmetry in them, where charge parity wasn't conserved
Okay.
the as a symmetry, and that combination of a very rapid change, non-equilibrium, plus having this charge parity asymmetry would lead you to the prediction that in fact you would actually have a change of from equal numbers of matter and antimatter particles to a large asymmetry,
Sorry,
or at least an
sorry,
asymmetry.
but maybe you just want to briefly explain like charge parity because we've heard and spoken about parity symmetry a lot, but never actually had an explanation. So maybe you want to do like just a quick, brief thing before you get
Sure.
back on track on charge parity symmetry and
Yeah,
why this
sure.
asymmetry is a
Right.
big deal.
Yeah. So charge symmetry means that, a positive charge will always remain a positive charge. And we actually have seen that. We don't have any evidence that charge, there is a failure of the symmetry of charge. The charge seems to be really preserved. Parity is, in fact, for every particle, they have a very specific parity, either positive or negative parity. The and you can think of it as actually whether in fact it's uh, the left or right-handed in terms of its behavior. The
Okay.
Now and parity itself appears to be preserved, but the product of charge and parity isn't conserved. In fact, there are some processes in nature where in fact this charge parity is violated maximally. In other words, that one process can't happen, but the other can. The
Hmm.
And this was actually discovered back in the late 1950s. The Won a Nobel Prize because it was something that was just completely not anticipated. But charge parity is not a true symmetry of nature. And so we actually see this what we call CP violation effects take place in a lot of different systems. The and the one that in fact we see it most very clearly was in the interaction of neutrinos and charged leptons. There you actually see that in fact everything has to be left-handed. Everything has to be left-handed. So it just means that there is no right-handed interaction that can take place. So that's actually the violation of charge, the CP violation, maximally as we talked about it. But there are other particles like quarks, like the bottom quark, that appears that doesn't actually conserve CP by the charge parity. The and it was and the discovery of that and that bottom quarks can turn into anti-bottom quarks. That's basically what CP violation really means. You end up then being able to use that as a way of predicting that in fact you had this could have this asymmetry in the early universe that with inflation would actually result in this baryon asymmetry.
Hmm.
And you only needed a small change because if you think about it, when the universe cools, if you have a small change in the small asymmetry between baryons and antibaryons, the baryons and antibaryons essentially annihilate each other and turn into photons. But if you have an asymmetry, you're just left with then a small excess of baryons. And that's exactly what we see. The
Hmm.
universe is filled with photons, And there's a very small amount of baryons that make up ordinary matter, the proton, the neutrons. That's what our universe is like. It's basically, most of it, almost all of it, is just photons.
So, wow. So we actually almost do have a theory for understanding baryon asymmetry.
We do, except...
So is this a theory, or is this like basically this is what happened?
No, it's still a theory.
Yeah, it's still a theory, right? Okay.
First, we weren't there.
Mm-hmm.
Okay, so let's actually be clear. We weren't there at the point of the immediate after the Big Bang.
Of course,
right?
We don't know.
Good. We don't know. But actually, more importantly, we don't know that there isn't actually a particular process, CP violating process, that's strong enough to actually give us the amount of CP violation we need to make the big inflationary model work. We have evidence that there are processes that do violate CP, the charge parity, but having one that's strong enough is still an open question. Now, with the discovery that neutrinos have mass, that opens up the possibility that, in fact, all of this asymmetry took place not in the baryon sector around quarks, but with the lepton sector. Between leptons and between the charged and neutral leptons. So that's an idea. It's another theoretical framing of it. That could actually get around the fact that among the quarks, we don't seem to have enough CP violation to actually explain what took place in the early universe. But a lot of the data is so consistent with this model that it's hard to get away from it. No one has come up with a better model for describing. So that's why we're stuck with it for the moment. But there are these questions. And by the way, it doesn't explain dark matter.